Welcome back. It's been a little while since our last video. Today we're going to talk about matrices. Now we've already seen these in the context of linear equations. We just picked the coefficients off the equations and put them in an array just like this here, right? That's one way we could create matrices. Another way is we could just simply put a bunch of numbers into an array like that. Or we might have a matrix that looks like this with variables in it. It's simply this rectangular array with entries. Okay? So what we're going to do is isolate these and talk strictly about them and try to make an algebra around matrices, like how they might add together or multiply together, that type of thing. But the first thing we have to identify is the religion of matrices, which is Roman Catholicism. Matrices are good Roman Catholics. Okay? This is how we remember the dimensions of a matrix. There's 3 rows in this and 4 columns. So when we report the dimensions of a matrix, we go rows by columns. Okay? This one, there's 1, 2, 3, 4 rows. Oops. There's 4 rows and 1 column. I just noticed now on the slide that this was a mistake. Totally intentional. It should be rows times columns, like that. Okay. Maybe it seems like we're just being pedantic in listing rows by columns, but it turns out to be quite vital in the arithmetic that we'll see. Okay, first things first. If we have a matrix here together with a scalar, I can multiply these two together. And it's a pretty simple operation. We just have to multiply everything by that. So here I go. Simply multiply everything by that. There's 2 times that matrix. Okay? And similarly, -3 times this, and you can fill in the rest. But it's just everything multiplied and so on. Like that. By the coefficient. Okay? We can also add matrices, but this is where that R times C business comes in. We have to make sure they're of the same dimension. So ask yourself, what is the dimension of this matrix? Well, there's 2 rows and 3 columns. What's the dimensions of this matrix? Again, 2 rows and 3 columns. Okay? So once these match, we can add together the matrices. And this is done in a very simple way, just like the scalar multiplication. I just add the corresponding entries. So I have -2 plus 1, 3 plus 2, 0 plus 1, 7 plus minus 3, 1 plus minus 1, and then 1 plus minus 2. Like this. Okay? And you can work that out. So these first operations are pretty straightforward. There we go. Pretty simple to do. Let's see what else we can do with matrices. Oh, here's some practice, which leads into something that we can do, something else we can do with matrices. I encourage you to try these, all of these, on your own, just to get used to those operations. And you only need to do as many practice problems as you need to get fluent with the operation. So you don't need to be doing all the practice problems here. But you should try some of these. So we would take 3 times everything here, plus this matrix, minus 3 times this. We could do this one. Take 2 times everything in here, minus 3 times everything in there. It's fine. When we get to this, you notice you have a problem. Okay? If I take the dimensions of A, well, that's 3 rows and 2 columns. But over here, G, I have 2 rows and 3 columns. Okay? Even though it has the same numbers making up the dimension, they're not in the same order. And this matters because I can't subtract G from A, right? If I started subtracting the corresponding entries, those two are fine, but then I would have something, which doesn't exist, minus 1. Okay, so that's where the problem arises, when those dimensions don't line up. Okay, and so you can check. We move on to the next one, a plus b. Again, we can't do it. Each one of these is of a different dimension, so we can't do that. It's just simply not defined. But here's something interesting down here. I ask you to multiply matrices, but how would we do that? Multiplying numbers is pretty straightforward. But matrices, how do we coordinate all those numbers in order to multiply matrices? Let's find out. So here I've got two matrices. This one has 3 rows and 2 columns. This one has 2 rows and 2 columns. It's always a good habit to identify the dimension of a matrix when you first encounter it. Okay. I want to multiply these two together, and sure enough, first we need to ensure our matrices are of the right dimension. Now what I mean by that is actually these two numbers. So the number of columns for A has to equal the number of rows for B. These two numbers have to match up. Okay? Once we have that, then we can multiply the matrices. We're going to do that now. It may look a little weird to begin with, but you'll get the hang of it. Maybe I'll do this. I'll first ask the question, what is the dimension of the resulting matrix? It turns out to be these outer numbers. So when I do multiply these numbers together, or these matrices together, I'm going to get a matrix over here with dimensions 3 rows and 2 columns. Okay? I'm going to leave this bracket off because I think the writing is going to take up a lot of space. Okay, so we'll find the entries in our matrix right now. I want to find this first one here, the first number here. And that's found by taking the first row of A and finding its dot product with the first column of B. Okay? So this first entry is the first row of A dotted with the first column of B. I'll just write these both as vectors like this. Okay? That's the first entry, so I actually have to do that. Maybe I'll do that right now. So I got 4 plus 0. The answer is 4. Okay. This next entry here, it's in the second row, first column. The way we find that is take the second row of A, dot product with the first column of B. Like this. Okay, and we can do that quickly. I've got negative 8 plus 3, so minus 5. This third entry down here is in the third row, first column, and I find that by doing the dot product between the third row of A and the first column of B. Okay. So it's actually really not too bad. The calculations, it's really just a bunch of addition. Okay. And 4, 1. It's really just a bunch of addition. It's not particularly challenging. You just have to get used to lining up the dimensions and then knowing which entry, how to find each entry, which rows and columns to dot together. I can keep on going over here in the second column, first entry in the first row, is going to be the first row of A dotted with the second column of B. Okay, and I'll just write that out because we're learning this right now, dotted with -2, comma 1. That's -2. Okay. And I'll stop there. You can finish writing out these two entries in the matrix multiplication. And that's it. That's how we find the product of two matrices. Okay. I leave some practice here for you. You can try it out. Oh, well, let's do one quickly. We'll do this. First, we have to check that the dimensions line up. So this is 2 by 2. This is 2 by 2. These two numbers match. That's great. So I can do the multiplication. And the result is going to be a 2 by 2 matrix, which are those two outside numbers. Okay. And so I do it. I'm going to do it a little quicker here. I'm not going to write out the actual dot product. Well, maybe I will for a couple entries. But you'll see that you can get quite a bit quicker at it with a little practice. So this first entry in the first row, first column, is going to be this first row dotted with this first column. So that's 3 plus 21. So that's 24. Okay. Now you try it and I'll just write out the numbers here and you can check against mine. So this second row first column is this dotted with that. So that's 2 plus 15, so 17. First row second column, first row second column. That's -3 minus 21, so minus 24. And sure enough, this next one is -2, minus 15, minus 17. Okay. You try those other ones, see if they work. Remember to check if the multiplication is actually possible. Okay, here we've got a 2 by 2 matrix, here we've got a 2 by 3 matrix. Check all of them before you do the multiplication. If the dimensions line up, you can't do the multiplication. Okay, let's keep on going. Here are some properties of arithmetic you might remember from times past. We have these things called associativity, which means we can add numbers together. We can choose which pair we add together first and then add it to the next, etc. Distributivity, also seen as FOIL sometimes. Commutativity, we can change the order of multiplication and addition of numbers, for example. That's what we have here. We have something called an additive identity, which means that when I take that additive identity and add it to any number, I just get that any number back. So it doesn't do anything in addition. And we have something similar to that for multiplication, which is called 1 when we're looking at multiplication of numbers. But that thing is called a multiplicative identity, so that when I multiply anything by it, I just get that anything back. Okay? And we have also inverses. For every number a, I can add a negative number, negative a, to that and get the additive identity back. And I can do the same thing here for the multiplicative inverse. I can take a, I can multiply it by the multiplicative inverse, and what I get back technically is 1, but what I get back is the multiplicative identity. Now, this may seem overly pedantic when it comes to numbers and identifying what type of operations we have and properties of those operations. But it becomes absolutely vital in matrix algebra to think in terms of additive identities and multiplicative identities and inverses and things like that. It's a big part of matrix algebra, and we'll see that coming up. One thing I want you to think about is if we have any of those other properties that we had for numbers, if we have those for matrices. For example, associativity. If you had 3 matrices, I want you to just think about this. Can I, for example, add the first 2 and then add the third, or can I do this? Would those give me the same values? Would they yield the same matrix? Think about that. If I have 2 matrices, is it true that I can change the order of addition like this? Or if I have any matrix like this, multiplied by a sum of two matrices, is that the same thing as A times B plus A times C? Do those matrices distribute in to the brackets? Can you think of maybe a counterexample of where that might not work? Okay. And what about matrix multiplication? Can we make it associative? Is it commutative? So if I had two matrices, can I multiply them in any order? Would that work? So let's look at that. Think about it, see if you can come up with any examples of where it wouldn't work. But ultimately, that's what we want to do with matrix algebra. We want to come up with all these properties that our number systems have and find analogs in the matrix system of algebra. Okay. So we want to do that, and we'll be doing that over the next week or two. Here's some practice to just try things out. I want to identify, so you can try out some distributivity, see if that works, or try to make it, evaluate this in two different ways and see if it lines up, etc. One thing I want to identify here, though, is this. Let's actually do that matrix multiplication. Okay, and I'm going to do this a little quicker. You can try it on your own and match it against what I have. So first row, first column, row, column. So this is going to give me 7. Now I'm going to move over into this next one. I've got 0. This next one I've got minus 36. Okay. Next, second row, first column. Second row, first column. And as I continue doing this, you should notice something. That multiplication left this matrix unchanged. I get that as an answer, is that same matrix. So if we think back to that previous slide, I've got this situation. I found a matrix so that when I multiply it by another matrix, I just get that other matrix back. What I found is a matrix that acts like the number 1. It's this one right here. This is a very special type of matrix, and we identify it as the identity matrix. Oops. The identity matrix. It's the matrix of an appropriate dimension so that when I multiply it by any other matrix, I get that any other matrix back. Okay? Here, for example, is a 2 by 2 identity matrix. Here's the 3 by 3 identity matrix. And you notice I just identify the dimension of that identity matrix with a subscript number here, like that. Okay? One other thing I should highlight is that the identity matrices that you see are always square matrices, meaning that the number of rows equals the number of columns. Okay? Or visually, they're actually physically square, right? This isn't a square matrix, this would be. Okay? Identity matrices will always be square matrices. This here is a 0 matrix. Some people might identify this as 0 with the subscript of the rows and columns, just to indicate the dimension. I didn't do that here. It's usually the case that you know the dimensions of the 0 matrix or of the identity matrix given the context. If you're working with a bunch of 3 by 3 matrices, you have an understanding that the 0 and the 1 or identity matrix are going to match that. Okay? Great. I think that's all we need to cover for now. Yeah. Go back through the slides, pick out those practice problems, give them a try, and we'll develop our matrix algebra.